Hello, welcome all. I'm Amit Daman, a remote sensing and GIS expert. Today, I'm going to start module 1, and our first topic is basics of Earth observation and types of satellite data. And we are going to cover in this topic, these are the content, and we are going to cover. And first, I will going to introduce what is remote sensing, or you may call Earth observation, and then types of remote sensing. There are different types of remote sensing I'm going to introduce. Then how remote sensing system works, and what are the content is the remote sensing system. Then I will going to introduce you about electromagnetic spectrum and what spectrum we can use in remote sensing or different type of remote sensing. And then most important part is spectral reflectance curve and atmospheric window I'm going to introduce. Then satellite characteristics. Definitely we have to know basics of satellite characteristics before going to learn about the satellite data. And then image resolution. Definitely this is a very important topic also, because as per the application we have to know which kind of resolution are important for the different kind of applications. And then image interpretation techniques, then types of satellite images, like we have different bands and platforms, and also different electromagnetic spectrum, and so wavelength. So we need to understand the type of satellite data basis on different bands, and then different applications of remote sensing. So what is remote sensing or Earth observation? So by the definition, there are lots of definitions. So I just generalize the definition for you. So remote sensing is the process of acquisition of data from the space. You can also add airborne aircraft, and without any physical contact. It means we don't have any physical contact between satellite platform or air-based platform with the earth or earth surface. So we are using electromagnetic radiations to acquire the data from the earth. So we are using satellite, we are using different platforms like airborne platform and ground-based platforms and satellite-based platform, or you may call space-borne platform, right? And then we are using electromagnetic spectrums to collect the data from the Earth surface. Then types of remote sensing. So basis of energy source, we have two type of remote sensing: passive remote sensing and active remote sensing. So you can see in the diagram, this is the sun, energy coming from the sun, you may call electromagnetic energy, which is directly coming to the earth and then reflecting to the satellite sensor. So that's how we are collecting the data by using the natural source. Natural source is sun. So we call it passive remote sensing. Then active remote sensing. Sometime we have cloud cover, sometime we have different kind of obstacle, and also in the night time we don't have sun energy. So in the daytime, what satellite do? Satellite just collect the energy by the solar panel or different kind of recording system, and then satellite just propagate the energy to the earth, and then energy back is scattered to the satellite sensor. So especially this kind of remote sensing we use in the night time or during the cloudy season. Yeah, this is the whole remote sensing system you can see in the diagram. So whole picture is telling the story behind the collection of data using the space technology or satellite based platform. Okay, you can see here, this is the sun. We can use some marker. This is the sun, and energy coming through the sun in a different wavelength. You can say cosmic, gamma, X-ray, ultraviolet, visible, infrared, microwave, radio wave. Right? This is the incident energy. We can also call it electromagnetic radiation. and then it has to cross the Earth atmosphere. So depends on different composition like particle size, gas particle size, and other particles which are available in the atmosphere. So this energy has to interact with those particles. So you can see here I draw some lines which is like it cannot penetrate this atmosphere because wavelength is too small as compared to atmospheric particle. So this is not important at all for the remote sensing. We need the energy until here, like surface of the earth, to acquire the data, right? So somehow ultraviolet can penetrate mid of the atmosphere, but it cannot reach totally on the earth, right? But visible, infrared, microwave, and radio wave can reach on the earth surface. So basis on this energy like visible, infrared, microwave, radio wave, we have different type of remote sensing systems, right? Like visible and different kind of bands also, you can say, like visible bands, infrared bands, microwave bands, right? And radio waves are very different kind of remote sensing. I will going to introduce you, but this is like radio wave especially we use for communication satellite, not for remote sensing, right? So then the energy coming to the earth surface, right? And then it is reflecting back to the satellite, and we have different type of sensors according to requirement. Like maybe we have the visible based band or sensor here, maybe we have infrared based, or maybe we have microwave based, right? So now this is just reflecting to the satellite, and then we have the different ground stations. Like this is the India I used, and we have a ground station here to collect the data from the satellite, right? Different countries have their own data collection center. So this is for India, you can say National Remote Sensing Center Hyderabad, right? And like data like I have example here for the different kind of electromagnetic spectrum, like visible spectrum, infrared, and microwave. You can see blue, green, red, these are like representing different bands, right? So in the whole picture we have two main elements, right? Data acquisition and data processing and analysis. So how we are collecting the data? Energy coming through the sun and reflecting back to the satellite, and then we are collecting to the earth base center. Okay, then we need to process this data and analyze according to applications. Okay, now I'm going to introduce you electromagnetic spectrum. As I told you in the last satellite slide, here this is the just a representation of the different electromagnetic spectrum, and now I'm going to introduce in detail. Okay, so this is the whole electromagnetic spectrum which is coming through the sun. Okay, so ultraviolet coming to the earth, but not onto the surface, it is just coming in between atmosphere. So it it's like not important to discuss. Then visible, of course, this is very important to understand. So we have to understand the different size of wavelength. Okay, so you can see the size of blue is 0.4 to 0.5 micrometer, then from 0.5 to 0.6 micrometer, then 0.6 to 0.7 micrometer. This is blue, green, and red. Then after it's near infrared. So here I have something to discuss. like energy in gamma, X-ray and ultraviolet region absorbed by the Earth atmosphere, hence not used for remote sensing, definitely. Then our human eyes are very sensitive. From 0.4 to 0.7 we call it visible range. Then yeah, remote sensing deals with energy in visible, infrared, thermal and microwave region, because this is the only part can come to the Earth and get back to the satellite sensor to collect the data. Okay, then definitely we have further divisions for the different purpose. So here we are going to discuss the different size of wavelengths. So the portion of the electromagnetic spectrum extending wavelength from 0.3 to 15 micrometer. So we call it optical wavelengths. So always remember, there is optical remote sensing and thermal remote sensing. Okay, basis on wavelength or electromagnetic region. Okay, so from 0.3 to 15 micrometer we call it optical wavelength region. Okay, then we have different reflective region inside of it. Okay, so reflective region is from 0.3 to 3 micrometer. So this is very important, because this portion is reflecting to the satellite or to the atmosphere. Okay, so this is the most important part to understand, which is providing the data, different type of data. So ultraviolet we already discussed, from 0.3 to 0.4 micrometer, then visible, then reflective or solar infrared, this is from 0.7 to 3 micrometer. Okay, so from 0.3 to 0.9 micrometer wavelength region is often termed as photographic bands. Like we use our ground photograph. So generally for the photography, we use 0.3 to 0.9 micrometer wavelength. Then we have emissive region. Like in the daytime, some particles in the atmosphere and Earth's surface collect some energy, then and observe some energy, and then they emit in the night time. So this portion lays between 3 to 15 micrometer. Okay, then electromagnetic spectrum specifically for microwave wavelength region. So microwave wavelength lies between 1 mm to 1 meter. So you can see this is very large wavelength, and definitely frequency is very low. So when we have cloud in the atmosphere, and definitely in the night time too, we use this microwave region to collect the data, right? So for the atmospheric study, for the monsoon study, for the uh, study for during the rainy season, this is like very important part of remote sensing. We need to understand. Okay, so definitely our particle size in the atmosphere is not that big, like 1 meter. So it can cross, or it can reflect or penetrate the cloud even. Okay, so microwave can penetrate solid and unconsolidated earth materials. So it can also propagate in some centimeters in the surface of earth. Okay, because of size. And this region provide an all-weather remote sensing capability, as haze we already discussed, cloud, rain, smog, hail or falling snow do not appreciable affect the radiations. Here now, spectral signature. So different objects have different properties. So how different kind of wavelength are reacting with the earth objects. So spectral signature, we have to understand how this wavelength and different kind of wavelength are reacting with the object, and how we will going to identify during our remote sensing analysis, right? Like interpretation techniques we will going to discuss. So in the remote sensing, basic property which allows identification of the object is called its signature. So for example, like we have different objects like papaya rip, and we know this is yellow, then the yellow color is the signature, showing that because our eyes are identifying the color as yellow. Okay, so yellow is a identity. Okay, so that identity of the color is signature. Okay, the basic assumption is that each individual has unique signature. Definitely different objects has different type of colors. Okay, or you may also say tones. Okay, we have 3 primary color, then 7 secondary color, then we have millions of different tone basis on mixing of primary colors, right? So each and every object have different signatures. Okay, right. So the knowledge of signature is essential for exploiting the potential of remote sensing techniques, and this knowledge enables us to identify the classify the objects and is required for interpretation of all remotely sensed data, whether the interpretation is carried out visually or digitally. Our eyes has some limitations, right? If we are going to try visually, definitely we have limitations, but by the digitally we use computer system and softwares, and we use different kind of values like digital numbers from the image to identify the objects. So definitely our eyes has some limitation, but digital platform doesn't have much like limitation like our eyes. So but we can use both, like during traditional methods we use visually, but nowadays digital is much appropriate. So this is the spectral reflectance curve. So how we identify and clear the signatures. Okay, how when we get the highest energy with the different objects. Okay, you're getting my point. Okay, so you can see this is the reflectance percentage. Reflectance percentage means like how much energy coming from the sun to the earth surface, and how much from the like 100% energy coming to the earth surface, and how much getting back, because we have different kind of interaction in the atmosphere like scattering, absorption. Okay, so but we need the energy which can go directly to the satellite. So how much going to the satellite, this percentage is showing that reflection. Okay, then we have the wavelength in micrometers from 0.4 to 2.6. Okay, then we have different kind of bands in between. Okay, these are like broad bands, not like very narrow bands. We excluded before 0.4 because gamma and ultraviolet, which are not needed actually. So here from 0.4, right, to 0.7, here I can mark here 0.7 micrometer. Okay, so this is the portion of visible portion. You can see the different color: blue, green, red. Okay, near infrared doesn't have any color, but I am using the red here to represent. This is in infrared portion, then this is the portion for mid infrared, okay, or far infrared, right? And these are the lines representing different objects. So we took 3 objects: water, vegetation, and dry bare soil. Okay, water is clear, we assume water is very clear. Okay, so this is the blue band. So where water has maximum reflectance, in the blue band definitely it has little low reflectance. If there is some vegetation, okay, if there is some vegetation in the water, then it is reflecting high, because clean water observe most of the energy. So clear water cannot reflect much. Okay, so this is the portion only for clear water, but if you have some sediments or some vegetation in the water, so it will reflect more. Okay, so we can also analyze clear water and we can call it dirt water, or we can say there is algae or something like this, and in the red portion there is nothing, it is going down. Okay, so this is the portion are very important when we are interpreting water, right? Then this is the line which is representing the vegetation, right? You can see the highest peak of the vegetation in the green band. Okay, when we use the green band, so definitely it has high reflectance in the green band. And dry bare soil, this is the brown color, is showing the dry bare soil. So dry bare soil has highest, this is the line, has highest reflectance in near infrared, then it is increasing in mid and far infrared, definitely. So this kind of reflectance showing the dry bare soil. Okay, so this is the whole picture you have to know during the interpretation. Then atmospheric window, like you have to understand very carefully atmospheric window, because electromagnetic spectrum has different energy, different wavelength. Okay, so they behave differently. Okay, so some part can reach on earth, some part cannot. So we have to know which part can reach or can cross the atmosphere and can propagate without any obstacles to the earth's surface and can get back to the satellite. Okay, so the colored area, this is the colored area, this colored area, oh, what's the wrong with it? This is the colored area which is showing reflectance, but some part in the between you can see it is not reflecting much energy. So if we are using these wavelength in the satellite sensor, doesn't have any mean. Okay, so in the visible portion all part is reflecting very well, so there is no problem. Even the near infrared, there is no problem, but somewhere in between short infrared and near infrared, this is short wave infrared, this is near infrared. Okay, there is some part which cannot reflect properly. Okay, and we have different gaps. So you can see in the table like how much region can reflect directly from 0.3 to 0.9. This is the visual range, can reflect from 1 to 1.0 to 1.1 near or reflected IR. Okay, so then you can see 1.3 to 1.4. Okay, there is a gap, there is 1.4 is missing, it means it is not reflecting. Okay, same here, 1.9 is not available, it means we don't need to use this wavelength in the sensor. Okay, so my mean is I want to make you sure only we have to use reflectance part, okay, which can go to satellite. Okay, this is called whole scene is called atmospheric window. Okay, now satellite characteristics. So we are going to discuss remote sensing platforms. We have different type of platforms like air-based, space-based, and ground-based. So the vehicle or carriers for remote sensor are called the platforms. This is the simple definition. So typical platforms are satellites and aircraft, but they can also include radio controlled airplane, balloon. Yeah, before traditionally we used balloons also, kites also sometimes for low altitude remote sensing. Okay, as well as lidar, light detection and ranging. Okay, it can use on the ground even. You can use a vehicle, ground based vehicle, to put the lidar, and it will collect the data from the ground. So you can say it light detection. We are using light source. Okay, and sonar, sound detection and ranging. Especially this sonar technology is useful for bathymetry investigation inside of the water. Okay, the key factor for the selection of a platform is the altitude. Okay, that determines the ground resolution, and which is also dependent on the instantaneous field of view. We call it IFOV of the sensor on board the platform. Okay, so remote sensing satellites and different airborne satellite purposefully has different heights, altitude. Okay, so this part also very important to understand. Okay, so first we are going to discuss airborne platform. Okay, so airborne platform and space-based borne platforms has been in use in remote sensing of Earth resources. Okay, in earlier days, aircraft were mostly used in remote sensing platform for obtaining photographs. We call it aerial photography, and the technology or methods by using the remote sensing from the photographs, it called photogrammetry, and this is different type of remote sensing. Okay, we are not going to learn this in this course because that topic is very different and methods are very different, but you should know about basics like if you are using the aerial photographs, you have to use photogrammetry. Okay, then Dakota AVRO and Beechcraft Super King Air 200 aircraft are currently in use. These platform currently used for the collections from the air. Okay, and aircraft operations are very expensive and cannot provide cost and time effective solution definitely because aircraft is only covering the very small area to collect the photographs, and it takes a lot of effort and it's too expensive and time effective. So this technology not that used nowadays. Mostly we are focused on space-based platform. Yeah, space-based platform. Yeah, platforms in space are very less affected by atmosphere drag. Right, there is no much obstacles, right, in because it is in space. Okay, so that's why it is very important. We have very less error. Okay, and entire Earth or any designated portion can be covered at a specific interval. Okay, that is the very good merit of satellite remote sensing. Okay, the satellite is a platform that carries the sensor. Yeah, definitely we have satellite and then we have different sensor on board in the satellite. Okay, and it is put into the Earth orbit with the help of launch vehicles. Okay, we have different launch vehicles to put the satellite in the space. The space-borne platform are broadly divided into classes. Two classes: low altitude near polar orbiting satellite. We also call it sun synchronous satellite because it's synchronized by the sun. Okay, and second one is high altitude geostationary satellite. Okay, so I will going to introduce in the next slide how these two satellites will work. Okay, so first you have to remember sun synchronous satellite is remote sensing satellite or Earth observation satellite. Second one is high altitude geostationary satellite. This is basis on communication. Okay, we don't have images from the satellite mostly. This is only used for communication purpose. So remote sensing satellite, we already discussed, this is space-based platform we use. Okay, so mostly we use the height for this kind of satellite, like sun synchronous satellite, from 700 to 1500 kilometer. Okay, this is not that far to collect the data from the Earth surface, right? Then the orbital plane rotate to the maintain precise pace with sun westward progress as the Earth rotates around sun. That's why we call it sun synchronous. Okay, since the position with reference to sun is fixed and satellite crosses the equator precisely at same local solar time, so the remote sensing satellite are synchronized with the time. How sun is crossing, from west to east. So same time manner, satellite also synchronized with the sun time on the earth. So satellite can collect the data very easily. So here you can see the animation of polar synchronous satellite. We call it polar synchronous also, sun synchronous also, because it is coming through north to south, pole to pole, and how it is covering the whole earth you can see. Okay, so that's how this satellite covers the whole, and it can repeat. Different satellite has different repeativity. It is coming the same point or same area in sometimes in 16 days and different side. It bases on satellite definitely. Okay, this is the beautiful animation. Okay, then we have another space-based satellite platform, right? That is geosynchronous orbit, or you can call it geostationary. By the name you can understand. It is satellite is not moving like sun synchronous satellite. It is fixed on a particular location. Okay, that's how communication satellite can work. Okay, and for the communication purpose, we don't need atmospheric interaction because these satellite use radio waves. Okay, so we use the height or altitude for this satellite about 36,000 kilometers. Sometimes it may be more, a little lesser, like 40,000 or 35,000 kilometers. Okay, so here the animation you can see how geostationary satellite work. It is like very focused on a particular location. That's how communication devices can work. Okay, now we are not discussing the geostationary satellite. I want to make it clear. So here we have different type of recording sensor in the satellite for the remote sensing or earth observation. So we have two type of recording system. Okay, and I can say in other words, our sensor also moving in different directions to collect data for the different purposes. Okay, we are not just collecting the 2D surface, we are also collecting the 3D surface. So sometimes we have to create the 3D. Okay, so definitely we have different purpose. That's why we have different recording system. Okay, so I just use one examples here, like the Indian remote sensing satellite payload collection of data based other satellite or other country also using the same recording systems. But here the animation I use from Indian remote sensing satellites. So we have two type of recording system: along track, or you can call it push broom scanning. Okay, and the cross track, like whisk broom scanning, like how you used a broom. Okay, so you can see the pictures here. I have the animation to show the along track or the push broom. Okay, so you can see the diagram, the same track we are using for the scanning. Okay, see, this is the satellite and this is the surface. It is just collecting along the track, collecting the data along the track. Clear? Okay, Now another one is cross track scanning. Here I have animation for it. You see how it is moving? It is just crossing the track. Okay, so this kind of data we use for the (3D) study, or create the 3D of the Earth surface. Okay, here we go. Resolution. Now we have data. You saw the satellite animations, how we are collecting the data. Now you have the data, but you have to understand the resolutions. So you know the how we remember the resolution. When you going to the market to buy the mobile, by the camera you always see, oh, we need 18 megapixel, we need 20 megapixel. Okay, so we are talking about quality. Okay, how much clear data or how much clear picture you are collecting from your camera, from your mobile, right? So that's how we have in the satellite too, but here in the satellite we have 4 type of resolution. Okay, here you can see spectral, spatial, radiometric and temporal. In the next slide I'm going to discuss in detail. Here we go. Yeah, spectral resolution. Yeah, you remember our different bands I introduced. Okay, so spectral resolution of remote sensing instrument, or you can call it sensor, is determined by the bandwidth. Okay, I can highlight here. Here is the bandwidth. Oh, sorry. Sometimes it's behave weirdly. Sorry. So these are the different bands from 0.4 to 0.5, right? This is blue, this is green, this is red. Okay, the peaks of these bands representing the intensity of the wave, right? This. So this is the band for the blue, this is for green, this is for red, right? So this is the spectral resolution. So if we use this portion, right, for the band, this portion I'm coloring. Okay, it is not reflecting much energy, but if we use only this portion, okay, this portion, this is reflecting much energy. So if we use narrow band, it means we will get more information. Okay, suppose we have 3 blue band, so it can improve the quality of the image. That's how satellite sensor work. Okay, the second one is radiometric resolution. Okay, we have 3 primary color. Yes, blue, green, red, and then we have secondary color. Okay, 7 vigor. Okay, we studied in our middle age. Okay, so suppose we have red colors. Okay, but we have different tone even, right? Orange, pink, right? These are also from the red color. Okay, but they are just tone of red color. So how much gray scale of one color you can identify from the satellite data? This is based on radiometric resolution. So that resolution based on byte, how much byte your data, your sensor has. Okay, suppose we have data only for, again there is a problem, sorry for inconvenience. Oh, what's wrong with it? Okay, so this is 255 grayscale level. So we have to keep power 8, means 8-bit data. Okay, if you increase 10-bit data or 16-bit data, okay, or 32-bit data, it means we have more shades of one color only. So more bit means more radiometric resolution. So radiometric resolution is determined by the number of discrete level into which signals may be divided. Okay, how much gray level one single color has, right? You got my point? You can see that here the gray level is lesser and here is more. Okay, so we can identify the objects more precisely in this data, not in this, right? Bigger the bit or higher the bit, it means more qualitative data. Okay, this is spatial resolution. We always talk about how much size of our pixel has, like we call sometime megapixel in our mobile camera, but here we have just a size of 1 pixel, like how much meter or centimeter covered by our 1 pixel in the ground. So if you have the bigger pixel, or you can say in other words, like just take an example. Okay, if you have 1 meter size of pixel, okay, so 1 pixel covering only the 1 meter area. Okay, and then you have 30 meter. Okay, so 30 meter area covering by the one pixel. It means 1 meter is more qualitative because we can see much information, zoomed information, like we have here for picture A, B, C, D, 1 meter, 10 meter, 30 meter and 250 meter. Okay, so you can see how much information is covering by the different satellite images. Okay, so 1 meter definitely it's more qualitative data because pixel size is lesser. It means more information. Okay, that's how spatial resolution works. Okay, temporal resolution. Uh, we we just discussed 3 resolution, which is depends on quality, but this resolution depends on time. Okay, so temporal resolution is related to the repeativity coverage of the ground by the remote sensing system. Okay, like we have one satellite. Okay, remote sensor data acquisition dates. Okay, so on the 1st June, the satellite crossing a one area, and then it is coming again on the same area after 16 days. Okay, on the 17th June. Okay, so the time interval of this satellite to come in the same area is 16 days. Okay, so we can do the phenomenal study, like how much changes over the 16 days already happened. So you can analyze the changes over the time, in the days, in the month, in the years, in the decades, because we have 40 years of data from the satellite now. Okay, so temporal resolution is very important for change detection studies. Okay, to analyze the changes. Okay, to analyze the phenomenal things like how much water uh, changes and how much vegetation cover has changes, how agriculture is reducing or growing. Okay, that's how temporal resolution works. Image interpretation. Okay, so image interpretation is the key to identify the different object in the satellite image. Okay, you see that around the world how we learn to understand the things around us. Okay, you see the structure, you see the texture, you see the pattern, you see the colors. Okay, like you have a lemon. Okay, so if the round things has a yellow color and size, you already know the how much size your lemon has. Okay, so you immediately recognize this as a lemon by the color, by the size, or by the pattern. It's a round. Okay, so that's how we have some interpretation elements. Okay, visually you can say. So first we go for color, or color has different tone definitely, then shape, okay, then size, then pattern, then texture, then shadow, then association. So you know some objects you need to understand by the association. Suppose you have road on the satellite image, and then you have the vegetation along the road. So sometimes we confuse what this line is representing along the road. Okay, okay, so we can easily understand by the road. Okay, only the vegetation cover can be there along the road. Okay, this is the association. Important part, types of satellite image. Sorry, I'm using my hanky again. Okay, so types of satellite image. We have different satellite images, depends on different bands. We discussed already about visible, infrared, and then we have different parts in these bands like blue, green, red, and then we have near infrared, mid infrared, short wave infrared, far infrared, and then microwave. Okay, so when we have visible, IR, or thermal, okay, in the single satellite, and when we have 3 to 12 band, we call it multispectral satellite data. Okay, here is some example. Landsat MSS, okay, multispectral scanner, then thematic mapper. This is another version of Landsat, and then enhanced thematic mapper. Then Aster, Indian remote sensing satellite, also has multispectral bands. Then ABHHR, MODIS. These are the another examples of multispectral satellite data, which is commonly used for the different applications. And then microwave, and microwave has radar system. Okay, so microwave definitely depends on the signals speed. So here, like, we have 1500 pulses per second. It depends on different microwave bands and satellite also. Okay, then we use the definitely cloud and darkness not an issue for the microwave remote sensing. Definitely we identify the feature by the shadow effects. Okay, and high resolution data has like very qualitative images. Like, suppose you have four multispectral band like visible and infrared. Okay, so it means there is one panchromatic mesh which is always belongs to high resolution. Okay, and mostly the highest resolution available nowadays is 0.30 meter to 1 meter. Okay, but they are very commercial, but you can see on the Google Earth they're using the high resolution to just observe the object. Okay, then airborne and spaceborne bit, definitely they have high resolution data. And hyperspectral, which is like very different kind of remote sensing, because it has like very narrow bands. Like blue band only has 100 or 200 bands, so it is providing more precise information, but they are very costly, and we don't need now for the study, and these are not open source at all. So these are the different type of satellite images. Here, applications where we can use the remote sensing or earth observation. Never forget, earth observation, remote sensing, representing the same things. Okay, so geology, definitely in the geology applications, they involve the study of landforms, structures, and the subsurface to understand the physical process creating the modified the earth crust. Okay, because satellite data can cover the earth surface, so we can find the different kind of changes, how different physical process taking the place on the earth surface with the time. Okay, So here are some bullet points I'm highlighting what kind of study you can do by using the remote sensing data in geology, like subsurfacial deposition, bedrock mapping, structural mapping, and sand and gravel exploration and exploitation. Okay, mineral exploration, environmental geology, sedimentation mapping and monitoring. Okay, in the river or in the river bed. Okay, and along the river you can also monitor the sedimentation and geohazard mapping. Yeah, there are many type of geohazards, so you can map by using the remote sensing. Then in the hydrology, very important. So when we study about the water science, so you need to understand the water on earth surface and weather, how weather flowing above ground. Okay, and frozen in ice or snow or retained by soil. So this kind of study we can do in the hydrology using remote sensing. And these are the following applications you can apply the remote sensing in the wetland mapping and monitoring, and soil moisture estimation. You can also estimate the soil moisture, and also can like uh, how they are evaporating and how much holding capacity your soil has. So we have that capability now. And measuring the snow thickness, definitely we can also study the volumetric study of snow or ice. Okay, then river and lake ice monitoring. Okay, then flood mapping and monitoring, river delta change detection. Okay, you need temporal data we discuss. Okay, so to find the changes in delta and river. Okay, drainage basin mapping and watershed modeling. This is the topic we are going to learn. Watershed modeling, definitely, and drainage basin mapping also, and irrigation canal leakage detection. Definitely this is the very important to detect the damage in the canal, so it can save the lots of lives. This is kind of hazard for the people. Okay, then land use applications. There are many. Natural resource management. Okay, you can identify what kind of land use and land cover over the earth by the remote sensing data. So you can manage, you can plan where you want to plant your tree, where you want your agriculture, where you want to create the settlements. Okay, and then wildlife habitat protection. Okay, then urban expansion, encroachment you can detect by satellite data easily. Routing and logistic planning for seismic exploration and resource extraction activities. Damage delineation, like from the 10 we have lots of disaster like cyclone, tornadoes, hurricanes, flooding, volcanic eruption, and seismic, and different wildfires also. So you can estimate the changes or damage, uh, right? And also legal boundaries for tax and property evolution. Many countries are using these kind of, like USA, India, and different European countries are using the taxation by using satellite data. And target detection, like identification of landing strips, roads, clearing, bridges, land water interface. Okay, these are the most important application. There are many, but these are the most important application. And references, these are the main reading you can find in the libraries. You can go to university, you can ask to people and subscribe these kind of book. You can buy these books also. These are very important reading to understand the remote sensing. Okay, and thank you very much for your kind attention. You can ask the question in form, and you can also email me. I will share my email, definitely, and you can see in my email in my introductory video too. Okay, thank you very much. Bye bye.